Okay. So here we are going to prove this theorem. Any system of forces can be reduced to a single force acting at a base point and a couple. So any system of forces is acting on some rigid body. Say this is R, this is rigid body. And so suppose n forces we are considering a system of n forces. So let S be the system having n forces, F1, I starting from 1 to there is F1, F2 up to Fn. Okay, so suppose this is the force F1, this is the force F2, and likewise you continue and get this is the force Fn. Say this is the point of action of F1, this is the point of action of F2, this is the point of action of Fn. So what we are supposed to prove here, this system, entire system of forces is acting on this rigid body. You can consider another system, or rather you will get another system of forces S dashed, which is equivalent to S. And this new system of forces will comprise of what? A single force. Okay. R, it will be acting at some base point and a couple. Okay. And a couple. This two we will get in S dash. We need to prove that this S can be reduced to this S dash. That means S and S dash are equivalent. We need to prove it. Okay. So for that thing out, let us see how we can prove that. Okay. So first and foremost of all, you are saying at some base point, that means some fixed point, right? So suppose this fixed point is somewhere here. This is your fixed point. Okay. We need to prove that our R will be acting at some at this base point, and we will be also getting a couple along with it. Okay. So now let us see how we can prove this. Okay. So first and foremost of all, let us consider a single, let us again draw this figure for the sake of simplicity. Let us consider this force, say F1. I just considered here two forces instead of considering so many forces. Just for the sake of explanation, you can easily extend it up to N. So these are these two forces, F1, F2 acting at P1 and P2. This will be the base point O. So once you are fixing the base point, you are fixing the position of P1 with respect to O. That means you are getting a position vector of this point P1, let it be R1. Similarly, for the P2 also, you are fixing the position of P2. So you are getting a position vector of P2 with respect to O. Now what we do, we insert or rather incorporate two forces F1 minus F1 at the same point, at the base point. So this was your F1, right? This was your F1. So let me introduce these two forces. This is F1 and this is minus F at the same point. So what you see, our event system was S. If we want to keep this system's effect unaltered, we have to consider some addition or subtraction of forces that will not alter the effect of the system, right? So what we are doing right now, we are considering two collinear forces of magnitude F1, but opposite in direction at the point O. So obviously they will cancel each other. So the effect due to F1 remains the same. Okay. So, and we have not altered the effect of S. Okay. But now we see if we insert these two forces, how we can use it for our purpose. You see the force of minus F1 at O, minus F1 at O, and force F1 at P1 are again two opposite in direction, equal in magnitude forces, but they are not collinear. So what? They will constitute now a couple whose axis will be passing through O. Suppose this is the axis. Okay. So now we are getting a couple formed by the forces minus F1 at O and F1 at P. At P1, sorry, not P, but P1. Okay, couple. Let the moment of this couple be denoted by G1. Okay. Now you see, we had the force F1 from the system S. Okay. Due to this force F1, we are now getting what? A force F1 at O and a couple of moment G1 whose axis is passing through O. But the force F1 originally, if we computed the moment of F1 with respect to the O and having the axis passing through this O, the moment of this couple would have been moment of this force would have been R1 cross F1 with respect to O, right? So Now, from this force F1, we are having two things. From F1, we are having two things. A force F1, initially it was at P1, right? Acting at P1. Now we are having from here, after inserting this F1 minus F1 at O, we are having F1 acting at O and a couple of moment R1 cross F1. Let me call it in short G1. Similarly, we can do the same things for any number of forces you are considering the system A. S. Okay. So that means here I have drawn for F2. So what you can do, you can just insert these two forces F2 and then minus F2 like this. And again continue the same argument. So for any system, any of the force, for every Fi, let me write in short, for every I, or rather for every I running from 1 up to n, you are getting ultimately two things. One is Fi acting at the base point O, and a couple, this is one thing, and a couple of moment Ri cross Fi whose axis is passing. Ri cross Fi is the moment of the couple whose axis is passing through O, axis passing through O. So ultimately what you are getting, if we are considering all the forces, you are ultimately getting all these forces acting at O. So you can easily add them up vectorically. So you will get some resultant force Fi. Let me call this R. So this is a single force you are getting. And what else you are getting? You are getting resultant couple, because all these couples will add up to get a single couple. We already know it from the theory that we have discussed before. So you will get resultant couple, say its moment be G, then it will be summation over I1 to N GI. That means it will be summation over this quantity and whose axis passing through the base point O, passing through O. Okay. So what we tried to prove, we have already achieved it, you see. We tried to prove system of forces given as. So, okay, that was comprising of n forces. We utilized it. It was reduced to another system which is having a single force, that is the R now, acting at the base point. OP is acting at O, and a couple, which is having the moment summation over Ri cross Fi. So this is it. We have proved yes, this is indeed possible. And this system, it is often written as like this: R comma G, because this is a combination of a force and a couple, okay, is often referred to as a dyname. Okay. Now you see at the point O, this is the resultant, and say this is the axis of the couple. Axis of the couple. Okay. So usually what can happen is this line of support of this axis and this resultant are not the same. So in general, for the Dyname, the resultant line of action, I am writing in short LOA of R and axis of the couple are not the same. Axis of the couple are not the same. In case they are same, for some systems they will be, and we will later derive the conditions for that. In case they are the same, we say this Dyname is reduced to a range here. Okay. So later we will just try to find out the conditions for reduction of a Dyname to a range. And once we find it out, this common line of action of this common line of support for this representing the line of action of R along with the axis of the couple, this is said to be the common line is said to be the Poinsot central axis. So we will find out later once we prove this range deduction, what are the conditions responsible for it, we will find out the Poinsot central axis equation. Okay. So, okay. So we have proved the theorem where we are reducing a given system of forces to a single force acting at some base point and a couple. So what will be our main motive? The system of forces will be given. So F1, F2, Fn are known. So once you are provided with F1, F2, Fn, you are provided with this capital X, Y, Y, I, Z, I. That means the components of these forces Fi. And also you are provided with the position vectors R1, R2, Rn, which you said. Here, these position vectors are I cross Fi. Okay. And this is the proof which I've already discussed. So I'm not going into the again the discussion of it. Okay. So you will get it from the PDF material only. So once we are getting this theorem established, so the explicit expression of the couple will go like this because we know how to calculate the couple summation Ri cross Fi. So we know how to calculate it. So explicitly once you break it, you are getting everything in the known quantities expression, everything in terms of the known quantities. Okay. So this is the moment of the couple which we need to derive because we are trying to characterize or rather find out what will be the Dyname. In any problem also, we'll try to do that. And further extension of it will be finding out the range that I already said I will discuss later. So this is a G. This is the resultant magnitude. And once the resultant magnitude is given, the direction is specified in terms of the direction cosines. That is easy to find out because you have this resultant and you also have the individual forces components. So this is the DCS of the R. Similarly, the magnitude of the moment you can find out once you have the vector itself. So once from here also, one thing I just mentioned here, so just for the sake of notation, we will use letter L, M, N are the DCS of G with respect to x-axis, y-axis, and z-axis. This is the most common terminology we will be using later. So DCS of G are given in this form. Okay.